All right, let's look at 5.2 homework. Number one, what does it mean to say the trials of an experiment are independent? So let's talk about what it means for the trials of an experiment to be independent. So, like if I'm flipping a coin 10 times, okay, a fair coin 10 times the same way, that would be the trials would be independent. So, what does that mean? Like, let's say I get heads on the first one. Does that impact what I would get on the fifth flip or the second flip or the 10th flip? No. So the outcome of one trial does not affect the probability of success on any other trial. So, like if I get heads on the first one, that doesn't change the probability of me getting heads on the second one. And then it doesn't change the probability, it has no impact. So, from trial to trial, there's no impact on the probability based on the previous outcome. So, that's what that means. For a binomial experiment, how many possible outcomes are there for each trial? So, let's think about in our notes. We might want our notes for this one. How many possible outcomes for each trial? So, we might be a little sketchy here trying to get this. So, how many outcomes are there possible for each trial? Each trial has exactly two outcomes, success or failure. So, like if I'm flipping a coin, it's either heads or it's not heads. I don't say heads and tails, I say heads and not heads. So, two, either success or failure. So, there's two outcomes. All right. Three, in a binomial experiment requires, or is it possible for the probability of success to change from one trial to the next? So if I'm flipping a coin, does the probability of getting heads change as I flip? Let's think about that. It doesn't. So in a binomial experiment, there is a fixed probability. Okay. The probability of success is the same. I'll show you real quickly in the notes. Each individual trial, the probability of success is the same. So from trial to trial, it does not change. Okay. So this in this case, does it change? You would say no. The success is the same for each trial. Okay. So now let's we did this on example one, the notes. Let's kind of unpack the fundamentals of a binomial. In a carnival game, there's six identical boxes which contain a prize. The contestant wins the prize by selecting the box containing it. Before each game, the old prize is removed and another prize is placed at random in one of the six boxes. Is it appropriate to use the binomial distribution? Find the probability the contestant who wins the game five times wins exactly twice. So let's think about this. Okay, so are the five trials independent? All right, first off, you either win the prize or you don't win the prize. So there's only two outcomes. Have the same probability for success. I didn't mean to click that. So what that means is that each time the contestant plays, will the probability of winning change? Well, if they win the prize, then before each game, the old prize is removed and the other prize is placed at random. So it's going to be one of the six boxes. So it's going to be a 1 in 6 chance every time. So the probability would be the same. And then would winning on the second one impact whether you win on the fifth time? Okay, that would not have an outcome impact on the outcome. So it is yes. The trials are independent. There's only two outcomes, and you have the same success. N equals 5, R equals 2, but this is wrong. I didn't mean to click on that one. It would be P equals 1/6 because you've got one selecting the right box, 1 out of 6 total options. So that one is a binomial. R is 2 because you're wanting to get the number of winning exactly twice. Now, let's explore how to use SALT. SALT will be your best friend on this, okay? And so let's talk about how we'll use that. So we're given an 8-question multiple choice quiz in a history class. Each question has 5 answers, only one which is correct. Since Richard has not attended class recently, he doesn't know any of the answers. Assume that Richard guesses on all 8 questions. Okay, so what's the probability of answer all questions correctly? So I'm going to go to SALT, okay? And I'm going to go to distribution calculators. Now, in chapter 6, we're going to explore the normal distribution. But for now, I want to explore the binomial distribution. Okay, and I'm going to have to fix some of this. I'll do that here in a moment. Okay, I'm going to pull this out so we can see it. Okay. All right, so I'm going to change this from trial to trial. Or yeah, here we go. From problem to problem, we can just look at this. Okay, binomial distribution. All right, what's the probability answers all 8 questions correctly? So what you're going to do is, how many trials are there? So how many questions are there? There's 8. The probability of success. Now, here's the thing. Each question has 5 answers and only one's correct. And he's just guessing. So what's the probability he gets it right? 1 out of 5, right? So 1 out of 5 would be 0.2. Okay. Now, this is what we're going to have to change. What's probably he answers all 8 questions correctly? So is all 8 an exact value or not? Is all 8 exactly 8? Yes. So I'm going to put equal because it's exactly 8. I must put equal to 8. Okay, so if you had 4 on there, you would put 4 trials because you had 4 questions, 0.2, and you put equal to 4. Okay. What's my probability? Well, I did 8, and guess what? My probability is really small. It's less than 0.001. So it is very, 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 very highly unlikely that he's going to guess all answers correctly. So I'm going to have to put 0.000. Okay, because it is less than 0.00. Now, would the zeros here imply that there's more values beyond this? If it was impossible, I would just put 0. But with the decimals here, this implies that there is a chance. It's just when I'm rounding 3 places, I can't express that because it's so small. What's the probability that he'll answer all questions incorrectly? So let's think about this. If the number of questions is 8, success is 0.2, what's the probability? What would the P be equal to for all incorrectly? He would get how many right? 0. And this would be an exact value because it's exactly 0 right. So exactly 0 right. So I'll put 0 in that spot, and I'll put 0.168. Okay, so it'd be a 16.8% chance he would get all questions incorrect. All right, C. This one's a pain. What's the probability he'll answer at least one of the questions correctly? Compute it 2 ways. First, use the rule for mutually exclusive events and the probability shown in the binomial distribution table. And then also use the fact that R greater than or equal to 1 is equal to 1 minus. So let me explain how this works. I'm going to have to pull up the binomial distribution table, and I'll explain to you how to read this. Okay. And you could use this for your values here. So what I'm going to do is, once I pull this up, I'm going to go, and I'm going to minimize this a little bit, but I'm going to zoom in. I'm going to go to n equals 8. So n equals 8. So 8. And my probability of success is, or R, I'm going to know the probability to get at least one question correctly. So at least one question correctly. Now my probability of success is 0.2. So at least one question correctly would be this value, would be getting 1 right, getting 2 right, getting 3 right. It'd be adding up these. Let me explain. I'm sorry, 0.2. I'm sorry. I made a mistake there. So it's an 8, or my n is 8. At least one right means I'm going to find the probability is 0.2. Probability is 0.2. And at least one right means I'm going to get at least, it'd be one of these values here. So it would be at least one of these. So I'd have to add up all these values right here. At least one right would be either 1, 2, 3, 4, 5, 6, 7, or 8. So I go to find the n, find the p, and I'm going to add up all the values one above. Okay, and I'll explain this here in a moment if you have 4. So it'd be 0.336. I'm going to do this so I can see it. Whoops. It's a little bit of a pain. So I'm going to start with 0.336 plus 0.294 plus 0.147 plus 0.046 plus 0.009 plus 0.001. Okay. And the other ones are 0. So 0.833. Okay. So that's my probability of getting 0.833. All right. Now, use the fact that P of R, that R is greater than or equal to 1, and do 1 minus P of R equals 0. So on this one, I'm going to find the n, 8. I'm going to find the probability, 0.2, and I'm going to do 1 minus 0. So 1 minus 0.168. So 1 minus 0.168 is 0.832. Okay, let me give you a little bit of guidance here. Let's say your value was 4. Okay, we'll unpack this some more. Let's say your value was 4. So if you had n was 4, your probability is 0.2. To find at least one, you add these 4 together. So 0.410 plus 0.154 plus 0.026 plus 0.002. So you add those 4 together. Oops, let me show. It's not wanting to show up here. You get 0.592. It won't show up on my calculator. So 0.592. Bad time to not work. There you go. So if it was at 4, if it would be 1 above, and then if you're doing the complement, you would do 1 minus 0.1410. 1 minus it equaling 0. So if you had 4, your first one would be 0.592, and your second one would be 0.59. So I think some of you have 8, some of you have 4. So that kind of gives you an idea to help you out with that because that's a little tricky. So for at least 1, you add up all the ones that are 1 above for that category, n equals 8, p equals 0.2. And then for using the complement, you just do 1 minus the probability that's equal to 0. Okay, now, should they be equal? What do y'all think? Yes, they should be equal, but they might differ because of a rounding error because those values in the table are rounded. Okay. Now, what's the probability that Richard will answer at least half the questions correctly? So now we're going to get out of this and we're going to go to SALT, at least half the questions correctly. So at least half. Let's think about that. At least half. Would that be above a number or below a number? Would that be at least half? Would that be above or below? Above, right? So if you're thinking above in math class, thinking higher, above higher is right, below is left. So we're going to click on right tail. We're going to click on right tail. Okay. And at least half, my n is 8, my p is 0.2. At least half would be how many? 4 and above, right? It'd be 4 and above. So it'd be 0.563. At least half would be 0.563. So let's hypothetically say you had 4. So if you had 4, if it was the number of questions you had, the probability of success 0.2, at least 4 would be 2 and above. So it'd be 0.181. Okay, 0.181. So that's how you would do that. So at least half would be half your questions and above. So you have to do right tail when it's at a place and above. Okay, so that gives you the answer to that one. Some of you have 4, some of you have 8. That's why I went through the 4 examples. Okay. Oh, I did that wrong. What did I do wrong here? That's embarrassing. Did I round wrong? 0.563. Oh, 0.56. Oh my goodness. 0.56. Oh goodness. I can't read. I apologize. It's 0.056. That was embarrassing. Okay, there we go. So that's why I click on the submit here because I'm sometimes wrong. I can't read there. All right, number 6. Before 1918, approximately 6% of wolves in the region were male, 40% were female. However, cattle ranchers in this area have determined the effort to exterminate wolves. From the 1918 to present, 70% of the region are male, 30% are female. Biologists suspect that male wolves are more likely than female to return to the area the population has been greatly reduced. So before 1918, in a random sample of 12 wolves, what's probably 9 or more were male. So let's think about this. I'm going to be on the binomial thing. And a random sample of 12 wolves, so that means my n is going to be 12. What's probably that at least 9 were male? At least 9, is that exact or not? Is that exactly 9 or is that 9 and more numbers? 9 and more, right? So now, 9 or more, would that be 9 and below or 9 above? A 9 above, right? So if it's 9 and above, we're going to click right tail. Okay, my probability of success before 1918, 9 were male. So before 1918, I'm using these numbers. So it'd be 0.6. And then 9 or above. So I do 9 here. And so you get 0.225. Okay, so I kind of have to unsort through all that and then I decipher it. Yes. So right tail, 0.6, my probability. What's probably that 9 or more are female? So I have 12. 0.6. Wait, I got to change my probability because now we're talking about females. So 40% are female. So that means my probability for success is 0.4 now. And then 9 or above are female. So it's still right tail, 9 above, 0.015. This is where it gets really tricky. The probability that fewer than 6 were female. Fewer than 6 were female. So let's talk about this. First off, I've got 12. My probability of success is 0.4 because we're talking about the females because that's the female probability. N was the number in my sample. Fewer than 6 were female. Now, fewer, would that be left tail, right tail, or equal? Is fewer below or above a number? Fewer is below, right? So it's going to be left tail. Now, fewer than 6. The temptation is to put 6 in here. Okay. Okay. So on the next one, we want the fewer than 6 were female. Okay, we got to be careful here because Fewer than 6 is left tail. Okay, we still have a sample size of 12. Probability of success is 0.4 because that's probability of success for a female. But fewer than 6. Let's think about this. What's wrong here if I put 6? It says fewer than 6. Does fewer than 6 include 6? No. So what should I put here? I need to put 5 there. So fewer than 6 means 5 and below. Okay, because if I put 6 there, it's got an equal to it, means it's including 6. So what you're going to do is you're going to put 1 less than that number because you're not including that number because it's fewer than 6. 6 is not fewer than 6, so 6 doesn't get to be included. So you have to subtract 1 from that. Okay, we're going to run through another example here, but we're going to do it with ones beyond 1918. So for the next set, we're going to go off of these percentages. Okay, from 1918 to present, a ram sample of 12 wolves spotted in the region. What's probably 9 or more are male. So there's 12 wolves in the region, 9 or more are male. 9 or more would be right tail. So right tail is 9 and above. Okay, right tail's at a point above. So that's right tail. So 9 or more are male. Now, what I've also got to do is change the probability of success. How many were male in that next one? 0.7. All right, just a moment. So I get 0.495. So this gives me 0.492 or 0.493. There's a lot to unpack here. I know it gets tricky, but if you figure out, SALT helps you out a lot. It really does. What's probably that 9 or more were female? So I've got 12. 9 or more. First off, let me change this to 0.3 because my probability of after 1918 being female is 0.3. 9 or more, well, I'm going to still use right tail because I'm wanting greater than or equal to 9. 9 or more would be like 9, 10, 11, and 12. So you're looking at the graph here, it'd be 9, 10, 11, and 12, okay? So the probability that it's greater than or equal to 9 would be for me, 0.002. Okay. What's the probability that fewer than 6 were female? So fewer than 6 were female. Now, fewer than 6, first off, I've got 12 in my sample. My probability of female is 0.3 after that. Fewer than 6. So is fewer, am I talking about at a point below or above? I'm talking about fewer than 6 is values below 6. So it's going to be left tail because left tail deals with values below a value. Now, fewer than 6, remember, the temptation is to put 6 there. But that is not correct because this is saying including 6 because this is less than or equal to 6. What you need to do is you need to put 1 less than that number in there because fewer than 6 would be 5 and below. Fewer than 6 does not include 6. 6 is not fewer than 6. So you would put 5 and below. This would mean 5, 4, 3, 2, 1. So you put 1 less than that number there and you get 0.882. Okay. All right. So on number 8, we have about 20% of people in America use a certain social media website. A group of 15 people, assume a random sample of people in America. What are the following probabilities? At least one of them uses the website. So let's talk about this. So at least one, 20% of people use the website, and I've got a sample of 15 people. So my N is going to be my sample size, which is 15 for me. My P is my probability, okay, which would be 0.2. Use a certain social media website. At least one of them uses the website. At least one. Now, when I'm thinking about at least one, am I thinking about one and to the one and above, or am I thinking about one and below? What's one above, right? So when you're thinking above, are you thinking left tail or are you thinking right tail? Which one's above, left or right? Right's above. So you're going to use right here. Now, at least one. Is one at least one? Yes, 1 is at least 1, so I'll put 1 there. So this at least 1 is greater than or equal to 1. You do include 1 because it could equal 1. This would be 0.965. More than 2 use the website. Now let's think about this. More than 2. Is that above or below? More than, above, or below? Above. So you're going to use right tail. Still 15 trials. Still 0.2 probability of success. Now, more than 2, the temptation is to put 2 here. But what's wrong with that? Let's think about this. Is 2 more than 2? Is 2 more than 2? No. So this is wrong because you want to do more than 2. So I need to do more than this. So more than 2 is not more than 2. So 2 does not need to be included. I'm including 2 here. That's wrong. I need to do one above that because more than 2 would be 3 and above. So you're going to put one above that on that one. So you're going to put one above 2. So you put 3 there. So 0.602. None of them use the website. None of them use the website. So let's think about this. Is that above? Is that left tail, right tail, or is that one equal? Equal, because none of them using the website means that 0 use it. So that means I'm equal to what? Well, at 15 trials, still the same probability. It's equal to 0 because none of them use it. You also could have hovered over this thing as well, this bar, 0.035. The graph could help you as well. 0.035. Now, this one throws you for a curveball. At least 13 of them do not use the website. Let's think about this. Do not use the website. So let's think. If 20% use the website, what percent do not use the website? 80%. Good. So what I have to do is I have to work with the complement here. So I'm going to work with the probability they do not use the website. Now, at least 13 do not use the website. At least 13, is that 13 above or 13 and below? Yeah, give me a value that's at least 13, 14. Well, that's above. So that's going to be right tail. If it's above, it's right tail. And I'm wanting to know the grade. Now, is 13 at least 13? Yes. So I include 13 in my value. So I get 0.398. Okay. And so that should give me my solutions.